How's everyone doing today? Excellent. Well, today we're taking a bit of a pit stop out of chapter 14 and moving over into chapter 16 for a minute. And I want to talk about parametric surfaces. So a lot of chapter 14, we've been dealing with situations where we have explicit surfaces. So explicit surfaces are cases where you have a z equals some function of x's and y's. And those are nice and everything. And it turns out, I mean, certainly if you're trying to develop the math, they're the easiest case. But there are more difficult types of surfaces out there. And in fact, if you wanted to talk about just some random surface that you find out in the wild or something, then it turns out explicit surfaces are rather weak. They don't have, they can't describe many types of surfaces. They're kind of the nicest types of surfaces. But if you just were to grab a surface at random, for instance, you know, when we talk about and we look at this donut, this torus is the nice mathematical term for that. You can't really write that so nicely as an explicit surface, as a z equals surface. You're going to have a ton of pluses and minuses and all that sort of stuff. Even if you wanted to write this implicitly, right? So if you don't have a surface that's a function, for instance, like the sphere is the nice one. So if you have a sphere, I mean, we can write it as z equals, but you need that plus minus sort of deal. The one step up for that is implicitly defined surfaces. So implicitly defined surfaces are typically where you have all of your variables on one side, and then you have a constant on the other. So if you have your x's and y's and z's all gathered up on one side, and then a constant on the other, these are called implicitly defined surfaces. And they're one step above explicitly defined surfaces. And you can do a few more things, right? So I mean, it is reasonable. You can write out the torus, for instance, as an implicitly defined surface. But if you really want to talk about surfaces in general and be able to develop math for surfaces in general, then really what you want is parametrically defined surfaces. So we had parametrically defined curves back in 13.1, 13.2, right? All of chapter 13, we were doing curves. And now we'd like to upgrade this and talk about surfaces. So instead of having one variable, right? Usually we use like t's. We could now need two variables because we have a two-dimensional object rather than just a line in space or a curve in space, right? We need to talk about a plane in space or some surface, right? That we maybe build out of paper or whatnot. So we need kind of two variables for the two dimensions that exist there. And so this has a nice parametrically defined torus here. I mean, in the pre-class videos, I did other things. This was another one that, again, you can see that the surface here is, I mean, it's complicated and whatnot, but you get this really crazy thing. So trying to find an equation for a z equals an explicitly defined surface would be darn near impossible for this. Implicitly is also very, very difficult. So really, if you want to develop some math for a type of surface, if you can find out ways to do things for parametrically defined surfaces, then really you win it. Because the parametrically defined surfaces, also you can basically get the implicit and explicit surfaces for free. You can easily make those parametrically defined surfaces very quickly. And so that's why we're kind of talking about for a minute here, parametrically defined surfaces. I guess in the pre-class video, we did this. We also practiced, you know, you can plug in specific values and then you will get curves on the surface. So for instance, we plugged in v was equal to 0 or u was equal to 0, and we got specific curves that lied on the surface. So it's the collection of all of the curves together that make the full surface. And if you plug in specific values, then you get just specific curves on the surface. So we can get a curve that maybe goes around the diameter or around maybe the equator here, or you could get, right, if you were to take some slice of this donut by holding maybe the u constant or whatnot. Then we started to talk about trying to come up with our own parameterizations. This is very akin to in 13.1 when we had, again, trying to figure out some parametric equation for some line of intersection, right? It was just a line or a curve of intersection. Here I would like to parameterize the full surface. And the bit here in the pre-class notes that I really wanted to highlight was that you have to be really careful about the wording for these things. You have to be careful about what are you trying to parameterize, what's the actual surface that you want to parameterize versus what are the bounds. Because quite often you have a couple of equations, and depending how it's worded, right, one of those is again the surface that you're trying to parameterize, and one of them is telling you why the surface doesn't go on forever. It's just some bounds that say we're going to stop here. So in 6.15, it was parameterize the portion of the cone. So the surface that we're interested in parameterizing in that case was the cone. Cones go on forever, right? If you don't restrict it, you're going to have an infinite cone, and then you can't really ask maybe many interesting questions, like maybe what's the surface area of the cone or whatnot. It's just going to be infinity. So you need to stop it at some place. And so this says we're going to stop it because we want it inside of this sphere. So we want it inside of the sphere of radius 2. So the actual surface is the cone, but instead of letting it go on forever, we're going to stop it when it hits the sphere, right? And so again, you have to be very careful about what is the actual surface that you're trying to parameterize versus what are the bounds? When do you stop your parameterization? And then I compared that to, again, very similarly worded. If you're going too fast, you may mix these up. Cases where you want to parameterize the sphere, and again, have that stop at some place. So that one, I mean, you can actually parameterize the entire sphere. We'll do that again in today's class with some of our notes. But if you want to stop at some place, you can also do that. So that's kind of the pre-class video in a nutshell. Any questions? Yes. Does this make 14.1 much easier? 14.1 is really a study of functions, right? When you talk about domain, it's domain of a function, right? And likewise, when you talk about range, it's range of a function. So all of that is with, we were already inside of the box of explicitly defined surfaces, right? We have a z equals some function of x's and y's. So it's not that this stuff will make that easier. It's just that this stuff really wouldn't apply. Good question. Yeah.
Example with the donut.
Yeah.
How'd you know that like R of B, that like that made like a vertical circle? So like that it wasn't X and Y.
Yeah, so when I could plug in specific values, right, for either U or V, and I just did this to kind of get some practice. So the question was, when I plugged in U equals 0 into my parameterization, you can see again me doing this right here, that instead of my full equation, which is up here, my x's, my y's, my z's, I plugged in everywhere I saw a u, I plugged in a 0, right? And so I got this equation down here once I did that. And now this is just a parameterized curve, right? Because now there's only one variable. When there's two independent variables, you're going to have a surface. When there's only one independent variable, then you're going to have some curve in space, right? So in this case, we can see that the y is constant. It's just 0. But the z is changing, right? Depending on what v is, sine goes up to 1 and it goes down to -1. Likewise, this 2 plus cosine v, right? Depending on what v is, that's going to go all the way up to 3 because cosine maxes out at 1. And it's going to go down to 1, right? Because cosine bottoms out at -1. So once you add the 2 there, again, 3 to 1 sort of deal. So this is going to give you, again, your x's. And I'm pointing over here to my little green curve, right? The x's go from 1 to 3. Maybe I can highlight this just for the video sake and whatnot as well. So my x's go from 1 to 3. It's a circle, but again, it's been shifted out by 2 in that x direction. The y is constant, right? My y is supposed to be the left-right stuff. I probably should label these axes, just good practice. So, right, y is there. It doesn't move to the left or the right at all. But then my z's, it does go up and down. But again, it bottoms out at -1 and tops out at +1. Does that make sense? These things take some practice. I understand that. Good. Any other questions? Yep. Yep.
I was wondering where you got the R equals 0.
Yeah, so the question was, when I was trying to find my bounds, right? So we were trying to parameterize the sphere, but it was this part of the sphere that lies inside of the cone, right? So that was the full question here. And so when trying to figure out what my bounds are, right, I need to know, well, when do I hit that cone, right? How do I represent that spherically? Because we had already decided that we wanted to use spherical coordinates to help inform our parameterization. And then I need to know, when does my sphere stop, right? When does it hit that cone? And so I was trying to figure out, okay, well, what does the cone look like in spherical? And in fact, we played this game in this section, 13.9, when we talked about cylindrical and spherical and a little bit about parametric surfaces for the first time, right? And so we did a question like this. And when we look at our spherical coordinates equations, right? So I mean, really, it'd maybe be better to start with this z equals the square root of x squared plus y squared. So here's what was given to us in Cartesian. When we did this for the first time in 13.9, I said, well, it's sometimes nice to pit stop into cylindrical. And so in cylindrical, we get z equals r. And then from there, again, we need to make our way into spherical because, again, we use spherical to help parameterize the sphere. And so I start to convert this, and then it seems like the heart of your question is, how do you get that r is equal to rho sine phi, right? So of course, the x's, the y's, and the z's, those are on the formula sheet, right? So you can just look at the formula sheet and you get those. So that's why the z equals rho cosine phi is maybe not up for question. So I would say there's a couple of ways that you can get this. First of all, you can draw all of these pictures, and that's what we actually did in 13.9, is that I drew pictures in order to justify why r is equal to rho sine phi. But you could also use the conversion equations. So for instance, right, I know x in polar or cylindrical should be r cosine theta. I also know, according to the conversion equations, that x in spherical should be rho sine phi cosine theta. So now if you just cancel out the cosines on both sides, oops. My iPad's going crazy. All right, there you go. Then you get that r is equal to rho sine phi. So this would be another way to redevelop it without having to draw lots of pictures and figure out the geometry of why, r is equal to rho sine phi. So this is a good way. But I think that if there's one more formula that you could remember as far as spherical coordinates, r equaling rho sine phi is a good one to remember. So right, a lot of it's given to you for free on the formula sheet. You don't have to have that memorized. But if you can memorize one thing for the spherical, I would say r equals rho sine phi is the thing that I would personally memorize. All right. Well, with that, we should probably move on to the new stuff for today. I guess I started talking about the math. I didn't even talk about kind of administrative stuff. What are you guys doing tomorrow in recitation? Yeah, some test review, right? So you're going to kind of go over some of the most difficult questions from the test. So we've identified a couple of those. Again, the average didn't really move much. Last time I checked, it was right around 77% still. So very good test one. So excellent job. Again, I hope everyone was at the average or above. Would be nice. I understand that's not realistic. You can't have an average where everyone's above it, but still, I hope that you guys were. And then, yeah, so Thursday's recitation, you'll largely be going over the test. And then, of course, you should look at this ahead of time. And if you have any grading questions, there's supposedly going to be some time at the end of recitation, maybe an extra, 5 or 10 minutes or something like this, that if you have grading questions, the TAs, the recitation leaders, right, they're the ones who take the first crack at doing the partial credit. So if you have grading questions, why you earned so many points, right, it's good to just talk to them in person. And so at the end of recitation, that would be an excellent time to do that. So yes, question here. Was the stuff that was on that test going to be on the midterm as well? No. Well, I mean, math builds on itself. So, I mean, there'll still be, there could be something about spheres, for instance, but we'd ask a different type of question. We're not going to ask for where's the center and the radius. We may ask something about a tangent plane to a sphere, right? So, I mean, math builds on itself, but we're not going to have, the focus is going to be solely on the stuff that we did after that first online test. So the midterm will be kind of the chapter 14, and once we get through that, a little bit of this chapter 16 stuff. But the midterm happens in recitation. So, once everyone gets seated and everything situated and everything gets passed out, right, you really only have 45 minutes. So it also needs to be a little bit shorter as well. So, right, we don't have the time to include the previous stuff as well. We need to kind of focus on the new stuff. Yeah. Yes. Is there a quiz tomorrow? No, no quiz. So, But yeah, so the quizzes and there's no quiz, there's no weekly review tomorrow. But that being said, I mean, you should still certainly go to recitation. All right. Well, that's all of the admin stuff, a little bit out of order. I apologize for that. But let's go ahead and jump into then the new stuff. So this subsection here, parametric surface time. And I did ask people if peanut butter jelly time was still a real thing before class, and it turns out maybe some people remember this. So if you do, please sing the peanut butter jelly time to parametric surface time. That's the intent there. But anyway, let's practice. Again, the main thing here I want to start with is getting some more practice parameterizing surfaces. And then we're going to do some calculus, right? I'd like to be able to calculate out some stuff with these parameterized surfaces. And that's mainly going to be the tangent plane. So we're going to need to get a normal vector in order to find a tangent plane. So very similar to what we did in 14.4 for explicitly defined surfaces, we're going to play the same game here today, but with parametrically defined surfaces. And along the way, right, we already talked about how you can plug in specific values and you get curves on that surface. So a thing that's going to be useful for 16.8, which talks about Stokes' theorem, one of the last subjects that we have in our course, you really need to be able to identify boundary curves. And so it's worthwhile, since we're here, to just talk about what boundary curves are and maybe how could we find some of those. So that's going to be the outline for today. All right, so parameterization. And I would like to parameterize this surface, and I have these bounds. So I've seen a number of these now, this z equals with a square root of x squared plus y squared. That 3 is going to be stretching it in the z direction a little bit, but ultimately this is going to be a cone stretched up in the z direction. So it's the positive square root, so it's going to be the positive cone. And we want it to go from z equals 0 to z equals 3. That looks like minus 3. Let's put it on the other side, and then it won't look like minus. So z should range from 0 to 3. Now, when we parameterize our surfaces, really, we're going to be stealing from what we know and love from our well-defined coordinate systems. So in 3 dimensions, we have, of course, the Cartesian. We have our x's, y's, and z's, and those are wonderful. We have our cylindrical, right? R's and thetas and z's quite often. And then we have spherical, rhos, thetas, and phis, right? So when I have a cone like this, or if I'm just, even if you don't see that it's a cone, right? When you have x squared plus y squared, you're probably thinking that behaves nicely or it fits well into cylindrical, right? Because x squared plus y squared equals r squared. And if you have the picture and if you can visualize it, right, you really see that it's circular as well. So all these sorts of things, right, are getting me thinking about, I would like to use cylindrical in order to inspire my parameterization here. So if I'm using cylindrical to inspire my parameterization, again, we need an x equals, we need a y equals, and we need a z equals in order to get our full parameterization. Now, in cylindrical, x is normally r cosine theta. Y is normally r sine theta. And z is just normally z. Now, the thing is, I need to have some x equation, some y equation, some z equation, and they can depend at most on 2 variables. So in here, I'm using s's and t's, but they don't get 3 variables, right? And so the fact is that I have r's, I have thetas, and I have z's, right? I have 3 variables, and somehow I have to figure out, using the fact that I'm on this cone, to somehow get rid of one of these variables. And so in this case, right, our cone equation is z equals, and if I was to, again, I'm thinking about cylindrical quite a lot here, this is equal to 3r, right? If I go ahead and replace it, and everywhere I see an x and a y with r cosine theta and r sine theta, then this simplifies very nicely down to r squared. Then you would take the square root and you just get r. Right? Or equivalently, on the formula sheet, you may just remember x squared plus y squared equals r squared. So again, you can swap that into r squared, take the square root. Again, in this class, we're only doing positive radiuses. So it's always going to be the positive square root, never a plus and minus when it comes to radiuses, either r or rho. And so that means z, since we're on this cylinder, we can go ahead and swap it out and put 3r. Now I only have 2 variables. I have my r's and I have my thetas. So it says we should use the notation, right? S's and T's, those should be our variables. And so I'm going to go ahead. Typically, I like T to be theta. You know, it kind of takes, start with the same thing. So I'm going to do S cosine T, S sine T, and then 3S. So now I have a parametrized surface with my parameters S and T, with my variables S and T. The other important thing that you always need for a parametrized surface is a domain. So again, T is taking the place of theta. What would you guess the domain of theta ought to be, or T ought to be, in order to make sure that we cover the entire cone here? 0 to 2 pi, right? So again, thinking about that this is coming from cylindrical, and this is a theta, it makes sense that we want to go all the way around our circle. So that means that we want to go from 0 to 2 pi. How about S? Well, again, S is taking the place of R, sort of deal. And notice that we do have kind of down here at the bottom, for instance, I'll use red. It doesn't look like we have much of a radius at all. And then as we go higher and higher, the radius for our circles, right, they get bigger and bigger. And they seem to max out here. Again, it looks like since we capped it at z equals 3, we need to figure out what our maximum radius is. So luckily we have this. Z needs to be from 0 to 3. And we know that z was equal to 3s. So we can transform that into some bounds for s instead. So for instance, when z was equal to 0, we can plug in 3s and solve then that s has to be equal to 0. So that's just saying at a height of 0, the radius of my circle was 0. And yeah, that makes sense. Now, as we plug in bigger and bigger z values, all the way up to our cap of z equals 3, and figure out, well, how big is my radius? Again, we can substitute in, instead of z, I'll write 3s, and I can solve, right? And that's going to give me s is going to be equal to 1. So my radius up here turns out to be, this is a circle of radius 1. So my bounds, again, if I don't want my cone to go on forever, I need to stop it at some place. And I'm going to stop it at a height of 1. So you can have the smallest radius is always going to be 0, because again, we don't allow for negative radiuses, but it's going to keep on getting bigger until we hit 1. Then we need to stop because that's going to correspond to a z value of 3. So this right here is the final answer, right? I guess if I wanted to really put it in the vector notation, r of st, it would be my s cosine t, s sine t, 3s, and you need the domain as well. So again, get in habit of writing the domain when it comes to these parameterizations. All right, questions? Oh, sorry, yes. So we are using cylindrical coordinates to inspire our parameterization. So this right here, I mean, we've talked about cylindrical coordinates kind of separate from this, right? If I was to write an equation like z equals r, this would be a perfectly fine surface that's written in cylindrical coordinates, right? When you write it as a parameterized surface, right, you need your parameterizations for x, for y, and for z. So you always need that collection. Sometimes we write them in vector form, like I did here. Sometimes you just write them as x equals this, y equals this, z equals this, right? But it's a little bit different than just cylindrical. Cylindrical coordinates or a cylindrical surface, z equals r, is kind of different than writing in the vector form. All right, well, let's go ahead and try another one. Maybe please take 90 seconds, 2 minutes at most. Try to find me a parameterization for x squared plus y squared plus z squared equals 9. I'd like your variables or your parameters to be S's and T's if you don't mind. What coordinate system do you think you're going to use to help inspire your parameterization for this one? Spherical. After all, x squared plus y squared plus z squared normally equals rho squared, right? This would look very nice in spherical. It's a sphere after all. Another 30 seconds. Get as far as you can. All right. So again, we're going to use spherical to help inspire our parameterization here. And that's because, well, we're on a sphere, right? It's a sphere of radius 3 centered at the origin. So x squared plus y squared plus z squared equaling 9. So you can either remember that from 12.1, or again, if you look at your formula sheet, you're going to realize, x squared plus y squared plus z squared is equal to rho squared according to our spherical transformations. So this is equivalent to, again, a sphere of radius 3. So our 3D radius should be 3. So when you transform this, you get rho equals 3. And this really helps, right? Because again, I only get 2 variables. I need S's and T's at the end of the day. Sorry, my pen decided to spaz out a little bit. So S's and T's at the end of the day. And yet in spherical, I have 3 variables, rhos and phis and thetas. But if I want to be on the sphere of radius 3, well, rho is equal to 3. So that means I can go ahead and swap out everywhere I see a rho, right? I'm going to swap in and give it a 3. So we'll have maybe x is equal to 3. I'm going to do sine s cosine t. Again, I usually like my thetas to be t's. Let's start with the same thing. So therefore, s is going to be phi in this case. Y is going to be 3 sine phi sine theta. Again, swapping out everywhere I see a phi and s. Everywhere I see a theta, I'm putting a t. And then finally, z is going to be equal to 3 cosine phi. And again, writing an s instead of a phi. So my parameterized surface looks like, just copy and paste now. And then we need to talk about our bounds. All right, so again, theta is taking the place, sorry, t is taking the place of theta. And so it's maybe not surprising that I would like our thetas to go from 0 to 2 pi. What if I had said all of this the same, but find the parameterization of this equation, the x squared plus y squared plus z squared equals 9, that lies in the first octant? If I was to add in those words, still the sphere and all that sort of stuff, but lies in the first octant, what would my bounds for t be in that case? Yeah? Exactly. 0 to pi divided by 2, right? Just like in our, if you were to draw this even in 2D, right? Theta, if you want it to be in the first quadrant, let alone in the first octant, right? You want to make sure your thetas range from 0 to pi over 2, right? So that's one easy way that you would get something besides 0 to 2 pi. I understand we've had 0 to 2 pi now twice in a row, so you may get tempted to say, oh, it's always this. It's a lot of the time, but not always. All right, and how about phi, right? S is taking the place of phi. In order to get the entire sphere, right, what should my bounds for phi be? Yeah, 0 to pi. So you need to be able to go from straight up to straight down in order to get all of the points on our sphere here. And again, if I was to add in those words in the first octant, right, then it'd be 0 to pi over 2, right, because you want to make sure you just get the top half. If you go beyond that, you start getting the negatives. If you're doing things right, then often your bounds for your variables, S's and T's, or the book also uses U's and V's. I usually think of U's and V's as vectors, but okay, they're not bolded here at least. But S's and T's, right, should not depend on one another. So notice that our bounds here, they don't have, like T doesn't have S's in it, right? The bounds for that, it just has 0 to 2 pi. And likewise, S here goes from 0 to pi. Now that's not always the case. This is not a theorem that says that they'll never rely on one another, but quite often for nice problems, you should have some nice constants there. All right, any questions so far? Yes.
Why is the parameterization not?
So the parameterization, because again, we're trying to parameterize x, y, and z, right? So anytime you need a parameterization in x, y, z space, you need an x coordinate, a y coordinate, and a z coordinate. And so it's because that our formulas for x, y, and z, right? And we can go back to our formula sheet, or even we can go back and draw pictures for how these things were developed, right? None of those have squareds in them. So if those had squareds in them, right, then yeah, we would certainly see, right? Because again, x is exactly this. We've just replaced a few things. So if we had sine squared phi or something like this, then yeah, we'd have sine squared s. But because we don't have any squareds in our parameterizations for x, for y, for z, and spherical, that's why they don't show up down here. Good. Yeah. Why wouldn't phi go from 0 to 2 pi? If you allow phi to go from 0 to 2 pi, you're going to hit every point twice. So then in that case, you're going to end up with, again, if I was to ask you something about surface area or something like this, you're going to end up having twice as much. So again, in our class, it's good to just remember phi always goes from 0 to pi. So let's suppose that, I don't know, I just want to hit this point maybe right in front of me, right? So that is, and maybe it's just one arm's length. So I'll say rho is equal to 1, right? So phi could be equal to pi over 2. That's my 90 degrees to get right in front of me. And then I don't need to rotate left and right at all, right? So theta could be equal to 0. So that's one way that I could achieve that point that's right in front of me. The other way, if you allow for phi to go from 0 to 2 pi, then I could point behind me, that's phi equals 3 pi over 2, and now use theta to rotate by pi. And then I can achieve that point twice. So that's, and it's the same thing like if you allow for negative rhos, right? I mean, having a negative radius in polar, like you did in calculus 2, it does technically make sense, but now you're running the risk of hitting points multiple times. So it's the same sort of reason why we restrict to only have positive radiuses. This is the same kind of idea of why we only allow phi to range from 0 to pi. It just kind of guarantees that we're only hitting our points once. All right, well then, another kind of a bonus about bringing up these parametric surfaces now is that later on, I talked about, I forget, maybe it was the first or second week of class that, this class, Calculus 3, it has a lot of hard stuff at the end of it. And, despite, no matter how you rearrange things, again, math just has this tendency of building on itself. And eventually we're going to get to this point where we're trying to calculate out flux. Flux looks like this. We're going to be doing surface integrals. This D capital S thing is complicated. We need to still talk about double integrals, and we'll talk about triple integrals as well. There's an equivalent here in triple integrals. We're going to have a vector field, that's this F thing, and then we're going to have N. And this N is going to be our normal vector to our surface. And so what we're doing here today is also taking some of the hard stuff that comes later on and bringing it a little bit earlier, right? So we're talking about, this is admittedly hard stuff that we're talking about in today's class. And it's so that way we don't have like an entire full week of hard stuff after hard stuff, later on. So that's kind of one advantage of doing this, moving things around so that we're talking about 16.6 a little bit here. So we're going to be very interested in finding normal vectors to surfaces. And so that's what I'd like to move into and get some practice now. So if we have a nice parametrized surface, you can parameterize it with U's and V's or S's and T's or whatever you'd like to, right? Then it turns out a nice normal vector is going to be given by if you get a couple of tangent vectors and then you take their cross product. So if you get a tangent vector, maybe in the U direction, and if you get a tangent vector maybe in the V direction, and if you take the cross product between those tangent vectors, you're going to get a normal vector. And one thing that we're going to do in today's class, right? And again, we're going to need to use this stuff just as part of a bigger problem later on. But in today's class, we can just ask for, let's try to find some tangent planes, right? Because tangent planes are relatively nice, but they need a normal vector. So we're going to ask for trying to find a tangent plane, and that's going to utilize our normal vector equation here. So I'm going to go ahead and parameterize this paraboloid for us. There it is. So U's and V's. I could have instead asked you to parameterize this. I need to give you the explicit equation, but you could parameterize this. And then, so here's the parameterization. I would like to ultimately try to find a normal vector. As we know, when you have a normal vector, there's multiples of these things. And so I'd like to try to get one that's upward pointing. So an upward normal vector. And then once we have that, we're going to come up with an equation of a tangent plane. So that's kind of the end goal here. Like I said, we're kind of quite close to, we'll need to be able to talk about boundary curves. And so I also want to talk about the boundary curve and figure out what the boundary curve is for this thing. So just like in the torus in the pre-class video, right? You're going to get curves on our surface when you plug in specific values for your parameters. So in this case, for U and for V. So for instance, if I was to go ahead and plug in U equals 0, this is kind of a test here. Well, then my only stuff left over would be V's. So I could say that this is some curve that has a parameter of V or a variable of V. And what this is going to look like is just 0, 0, 5. Again, I'm plugging in 0 everywhere I see a U. So this is talking about at the top here of this paraboloid. Elliptical paraboloid here. So this is the very top. So this isn't quite our boundary curve. The boundary curve, right, is going to be anywhere the surface kind of abruptly stops, right? So if I was to build this out of paper, right, where is the edge of my paper? So there's not really an edge near the top here because this would just be kind of continuous paper. The boundary curve is going to be down here where, again, the paraboloid would normally kind of go on forever, but we've stopped it, right? We've cut it. And this right here is where our boundary is. So this is the curve that I'm interested in finding. So you could try to plug in our other values, and quite often you're trying to plug in these things that are at the bounds of our parameterization, right? The bounds of our parameterization quite often refer to boundary curves, right? Because they're just kind of on the outskirts. So we already tried U equals 0, and that wasn't 1. It was at the very top. What if we tried U equals 2? That's the other boundary, at least for the u's. In that case, my equation would look like 2 cosine v, 2 sine v, and then 5 minus 4 would be 1. So at a height of 1. So these are now, let's see, maybe you recognize this from polar. This looks like a circle of radius 2 to me, but it's being lifted up, right? It's at a z value of 1. So it's a circle of radius 2. I'm thinking about r cosine theta, r sine theta, but it's now at a height of 1. And maybe it's a little bit hard to see in this picture, but yes, this is supposed to be at a height of 1 here. So my boundary curve is exactly this. And again, in order to get it all the way around, we'd still allow for v to run from 0 to 2 pi. So boundary curves are just plugging in specific values into your parameterized surface, usually the bounds. And right, at worst case, you're going to have to plug in 4 things if you get very unlucky. As you do more and more of these problems, you get some intuition for them, I find. And so you only maybe need to try 1 or 2 typically. All right, but let's get to the meat here, and that's going to be this upward normal vector. So I'd like to find the upward normal vector at a particular point, and then we can use that to come up with our tangent plane equation. So upward normal vector, again, I'm going to need to take a cross product of my tangent vectors. So let's go ahead and first calculate out some tangent vectors. So I need to take a partial derivative first with respect to u. So I'm going up here and I'm looking at my parameterization, and I'm thinking about taking a partial derivative with respect to u, and that means that v is constant, right? So if I take the derivative with respect to u, I'm going to have 1 cosine v. If I take the derivative with respect to u here, I'm going to have 1 sine v. And if I take the derivative with respect to u here, I'm going to have negative 2u. So there's my partial derivative with respect to u. With respect to v, let's see, I'm going to have what? The u's along for the ride. And when I take the derivative of cosine, I'm going to get negative sine v. Likewise here, the u's along for the ride. When I take the derivative of sine, I'm going to get cosine v here. Lastly, 5 minus u squared. That doesn't have any v's. It's all constant with respect to v. So when I take the derivative, I'm going to get 0. I'm about to take a cross product. You can take a cross product of this with all these nasty formulas in it, right? We've come a long way since 12.4 when we first did cross products with just numbers, right? You can do a cross product with all these nasty variables and all that sort of stuff in it, or you can take the easy route here and you can plug in your values sooner rather than later. So it does work out. You can wait and plug in those values later, but now that we've taken the derivatives, we can go ahead and plug these things in now, and then life will be a little bit easier for us. So I'm going to, everywhere I see a u, I'm going to plug in 1. Everywhere I see a v, I'm going to plug in pi over 2. So cosine of pi over 2 is going to be 0. Sine of pi over 2 is going to be 1. And negative 2 times my u value is 1, so that's going to be negative 2. Next up, we're going to have what? Negative 1, 0, 0. So now this, I think it's easier to take the cross product of. I's, j's, k's, 0, 1, negative 2, negative 1, 0, 0. Stuff with i's minus stuff with j's plus stuff with k's. Crossing out our first row, first column. Looks like we got 0 minus 0. It's pretty nice. Cross out our first row, second column. Looks like we got 0 minus, and then negative 2 times negative 1. So that's going to be 2. There's a ton of negatives here. And then finally, when I cross off my first row and third column, it looks like I'm going to have 0 minus negative 1. So 0 plus 1. So my normal vector here is going to be 0, 2, 1. Now this is indeed a normal vector. Check. Is this an upward normal vector? And how would I know? So if you had to put a mathematical equation behind the word upward, what would you say a mathematical equation behind upward would be? Sure, positive z, right? So z should be positive if you want it pointing upward. Because I mean, when I have my surface here, and I don't know exactly where this point is, right? But let's suppose it's right here. I could have a normal vector, right? That's at, again, it's going to be at a nice 90 degrees to this. I could have a normal vector that's pointing this way, and that's, or I could have a normal vector that's pointing kind of inside of this, right? Both of them are at 90 degrees to my surface, but only one of them has a positive z component, right? So I look at this and I see that I have 0, 2, 1, and the fact that my z component is positive means that I'm happy. What if that was a negative value right here? What would I do in order to force it to be positive? What am I allowed to do in order to get normal vectors? It's close, but yeah, so we need to multiply by -1. Yeah, so yeah, that's kind of what absolute value does to just specific numbers. So yeah, we need to multiply by -1 because technically, right, I mean, I did u cross v, but there's no reason that I couldn't have given you a formula that was v cross u, right? I mean, why did I say u is special? Why did u have to go first? What if I want v to go first? This will still make normal vectors, right? But now the only thing is that they're going to be pointing in the opposite direction. So in this case, they'd be pointing maybe in this downward direction here rather than the upward. So really you can have plus or minus related to any of these normal vectors, right? Scaling a normal vector does not make it not normal anymore. So you can multiply it by 5, you can multiply it by -3, right? These are all going to be examples of normal vectors. Some of them will have positive z components, some of them will have negatives, right? And so you can just force it to be positive by multiplying by -1 is typical. All right, last bit here, find the equation of the tangent plane. Anytime you want a tangent plane, or really a plane in general, right? You're going to have our classic plane equation. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. This is the standard equation for our plane. It has a normal vector of a, b, c. I just figured out that I want my normal vector to be 0, 2, 1. So I'm going to plug in everywhere I see my a, b, c. I'm going to plug in 0 and 2 and 1, respectively. The last bit is that I need to know my point that I'm attaching my tangent plane to. So I need an x, y, z triplet, right, that somehow corresponds to this special point that I want to attach my tangent plane to. Well, luckily, back in my original equation, this gives me x's, y's, and z's if you have a u and a v value to feed it, right? So in this case, I know that u should be equal to 1 and v should be equal to pi over 2, and this will output the x, y, z coordinate that I want to be at. So let's go ahead and plug in 1 and pi over 2. And let's see, cosine of pi over 2 is 0. Sine of pi over 2 is 1. And again, u is supposed to be 1 in this case. So I'm at the point 0, 1, 4. So my x coordinate was 0, my y coordinate was 1, my z coordinate was 4. So 0, 1, 4. And there is my equation of a tangent plane. It's a plane, certainly, and it's got the right normal vector to be tangent, and it's pinned at the right spot. All right, well, I see that it's we're out of time. As is typical, I guess I like to have too many problems than too few, but please do try this one. Very similar to our last one. And then I'll post the solutions to this here on D2L after class. So I'll stick around if there are any one-on-one questions. Otherwise, I hope you guys have a great rest of your Wednesday. I hope you go to your recitation and double check and see how you got graded for your test. And then I'll see you guys Friday.